Okay, everyone, I've got a problem here for you to try out just to get started for today. I'll give you about, I don't know, 5 or 6 minutes, see how you do. I put the work up here so you can see it. Okay, do we need to talk about this at all? Anybody have any questions over the derivative itself? In yellow, any questions on that? Chain rule, right? The derivative of natural log of anything will be 1 over that anything, whatever it is. And then chain rule says times the derivative of what's inside, which is your 2x minus 4. in parentheses, must be in parentheses. And then you just plug in 4 for x, and you get the actual slope of the tangent line, which is 4. And then you just use your point slope formula for the equation of the line. So y'all are all happy with that? So here's the graph of that function. And what we just found was the equation of the tangent line at the point 4, 0, which is right here at this point. So let's see if we got it right. It was 4x minus 16. Yeah, 4x minus 16. There it is. Okay. Any other questions that you might have over homework or anything else? Something I can clarify before we move on? We're okay? Everyone happy? Okay, we are going to continue the same section we just were covering last time. And the major results from last class, I'm going to summarize them here, was that if you have e raised to, I'm going to say u instead of x, and you take the derivative, you will get e to the u itself, but then you will always have to do chain rule and multiply times the derivative of what was up here. So that's just another way of writing the formula from last class, but taking into account the chain rule. That if this is x, then of course this is just 1. But if this is something other than x, you still have to take the derivative of it. The other thing we learned was that if you have a raised to the u, so this time the base is just some number, not e, that the derivative of that will be itself times natural log of a, then times the derivative of what was up there. So again, this is the chain rule happening here, but when it's just a general number, you have to put the natural log of that number right here. Okay, so those are the two main formulas for exponential functions from last time. And then we have the natural log. So if we take the natural log of u and we take the derivative of it, you will get 1 over u times the derivative of whatever that u was. So that's the problem we just did just now. And then if you change that log to just some arbitrary log where it's not base e, the derivative changes to be 1 over u again, but you've got to put next to it times natural log of a, and then chain rule, you'll always have the derivative of what was inside. So those are the main, I guess, 4 formulas from last class. And so now what we do is we are going to learn a very important type of differentiation called logarithmic differentiation. So I'm gonna start with a very basic example, and then we'll kind of build from here. All right. So when it comes to logarithmic differentiation, there's kind of 2 different types of logarithmic differentiation we're going to do here today. There's 2 different types. So the first type is the one I'm about to show you. Let's say we have something like y equals natural log of x squared plus x plus 1 raised to the 5th power. So that, that 5th power, it's very important that you understand that 5th power is only acting on this parentheses. So it's only acting on this right here. It's not acting on the natural log. If I wanted it to be on the natural log, I would have had to have written it this way. I would have had to have another set of parentheses and then a 5 here. So these are not the same thing. Do you all see the difference between the 2? Any questions on that? We are not doing this right now.
I have a question. So you know,
Yes.
with our notation with sine and cosine, we can just put the power like right next to the sign.
Uh-huh.
Can we do the same thing with natural log?
You can do the same thing with natural log. So you would do it for this one. It would be natural log. You could put the 5 here, and then x squared plus x plus 1 like that. That would mean this. Yes. But it does not mean this. That's all I'm trying to make sure we're clear on, is that the 5 here in the parentheses here means that this is all, you can almost look at it this way. This is all sitting inside the natural log like that. Okay, now one way we could do this, I'm going to show you one way, but I don't want you to write this down. This is just one way we could approach this problem. We could say, all right, the derivative of natural log of something, right? This is chain rule. The derivative of natural log of all of this will just be 1 over all of that. Okay, so that's just the derivative of natural log of all of this junk is just 1 over all of that junk. But then I have to say times, now I'm ready to take the derivative of everything that was in here. And for that, I do chain rule because I have a 5 out here. So I bring the 5 out front. And then I have x squared plus x plus 1 to the 4th. Now I've taken care of the 5. So now I say times, and now I go in here and take derivative of what's inside, which is in parentheses 2x plus 1. Okay, does everyone see that's an approach I could have used? Yes? But this idea of logarithmic differentiation, what it does is it allows us to take advantage of properties of logs. So let's revisit the problem again. And I'm going to put a parentheses around here just to kind of illustrate again something important. I'm going to bring up the properties of log from college algebra that I showed you last time. I'm going to show you one property in particular. This is from 3.2. There was one property in particular that I told you was really important. It's this one right here. It says if you have any log, it can be natural log or log base 2, any log that you ever are looking at. If you have something raised to a power inside the log, you can always just drop the power out front and put it in front like this. That has nothing to do with derivatives. That just has to do with properties of logs. So if I go back to this problem, I realize I have log of something, and that is all being raised to the 5th power. So by properties of logs, I can bring the 5 out in front of the log. 5 natural log x squared plus x plus 1. Okay, that is a property of logs. Now let me take the derivative. So if I take the derivative now, the 5 is in front of this and it's being multiplied. So we've already learned that when you have a constant in front of a function, you take the derivative, the constant just comes along for the ride. So I can just bring the 5 with me and then say times, now just take the natural log of this. Or sorry, the derivative of the natural log of that, which is going to be 1 over x squared plus x plus 1. That's the derivative of the natural log. And then you have to say times the derivative of what's inside, which is 2x plus 1. And this is our answer. We could, if we want to, we could write that as 5 times 2x plus 1 over x squared plus x plus 1. So I just slid this on top and slid the 5 up here on top and got this answer. And notice that this answer is much cleaner than this answer, but they are the same. And you can see they're the same because this one is raised to the 4th power, right? And then you have the same expression on the bottom to the 5th power. So you could cancel all 4 of these and cancel that 5 and let it become a 1. And now you have 2x plus 1 over this, and you still have a 5 out here, which is exactly this answer. You'll see that? So all that did was saved us a little bit of chain rule, right? By doing that. Any questions? Let me show you another illustration of this logarithmic differentiation on a different problem.
Sorry, quick question.
Yep.
Will you ever ask us in like tests or homework to reorder it like you just did? Or the
You need
example?
to do this way instead of that way?
Yeah, will you ever ask us to reorder it?
So will I ever tell you use this property of logs instead of doing it the old-fashioned way?
Yes.
I won't tell you, but let me show you a problem, okay? Let me show you a problem where you will want to, all right? Like this is just your first example. I'm building up to something here. So let me give you another problem where you're going to say, oh, you know what? I should probably use properties of logs, okay? So take a look at this one. Y equals natural log, get ready for this. In parentheses here, x plus 1 to the 7th power. Then how about 2x minus 1 to the 4th power? All of that on top of x squared and then x cubed plus x to the 8th power, close parentheses. Okay, so Brian, you look at this and you're like, shit, right? Looks like a disaster. Because think about what you'd have to do. You would have to say, okay, I have natural log of something, right? So the derivative of that would be just 1 over all of this. Agreed?
Yes.
But then you'd have to multiply that times the derivative of what's in here, which is quotient rule.
Yeah, f over g.
F over g, but your numerator f is a product rule, but each of those require chain rule. Do you see that?
Yes.
And that's going to be a mess, isn't it?
Absolutely.
Okay, so before I even start the problem, I'm going to just do some algebra first. I'm going to do this first. So see if you like this or not. Well, don't tell me if you like it. Tell me if you understand it, what I've done here. Okay, can anybody tell me what I just did?
Well, if ln is equal to 1 over x, then wouldn't that mean 1 over x is like negative ln? Or something?
Natural log of x is not equal to 1 over x. The derivative of natural log of x is equal to 1 over x.
One of the properties of logarithms is that a log with the divisor inside of it equals the log minus that log.
Exactly. So look, very important. I'm not taking a derivative right now. Okay, let's be very clear. I'm not taking a derivative. I'm using algebra right now to rewrite the problem, and hopefully when I'm done, it's going to look better and my differentiation is going to be easier than had I just tried to brute force this from the beginning. So the property I'm using that Cody brought up is this property. With logs, you have this property that if you have natural log of x divided by y, that it can always split up to be natural log of x minus natural log of y. That was a property I showed you last class. And I told you all that these properties are algebra properties and that you should remember these from college algebra because we may use them. Well, we're going to use them, and I'm using them today. Okay, so if you have log of division, it becomes 2 logs with subtraction. So that's the first thing I did. I looked at the numerator as being like an x and the denominator is a y, and I rewrote this as natural log of x minus y. You'll see it?
Yes.
Back in college algebra, this was called expanding a log expression. In college algebra, you should have had to have done this. Okay, now that I'm here, I'm going to realize that in the first log, I actually have multiplication right here. Now look, I'm not taking the derivative yet. Okay, I'm not taking the derivative. I'm still just doing algebra. Go ahead, Dilpreet.
Why the power is 8, not the 4?
Oh, yeah, sorry. This right here should be a 4. I'm not sure why I wrote that. I've been making all sorts of little mistakes today. It's weird. 7. Okay, thank you. Is there everything else right?
Yes, sir.
I think it is, yeah. Okay, so still using properties of logs. I realize I have a log and I have something times something. So I'm going to use this property that if I have multiplication inside of a log, it splits into 2 logs with addition between them. Again, one of the properties of logs that you need to know. So let's go ahead and do this. Y equals, okay, everything in yellow is going to turn into 2 logs. The first log is going to be natural log of x plus 1 to the 7. And then what?
Plus natural log of
Plus ln.
Plus, right? Plus, I have a plus sign. Natural log of now the next piece, 2x minus 1 to the 4th. That makes sense? What about the other log? The log that was in green?
then it's gonna be minus
See that product again in between the x squared and the x cubed plus x to the 8th? We have another product there. Not the product rule. I'm going to use the property of logs that I'm going to expand it out. Now, what about this minus sign? This is very important here. That's a minus, right? But since this thing in green is going to split into 2 pieces, right? It's going to split into 2. I need to put a big set of parentheses here so that that negative will get distributed through to those 2 logs. So my first log is natural log of x squared. And then plus again, natural log of the x cubed plus x to the 8th. All right, y'all okay with that? No derivative yet, right? I haven't taken the derivative. All I'm doing is using properties of logs. Next thing I'd like to do is distribute this minus through. So it's going to put a minus in front of that and a minus in front of that. And I'm going to do that on the next line, but watch what I do now. Check this out. Okay, do y'all see what I did? Use that other property of logs that says if you have natural log or any log of something to a power, the power can drop out front. So I dropped the 7 out front. I dropped the 4 out front. Here I had a minus, but then I dropped the 2 out front. Here this minus came through, but I dropped the 8 out front. And at this point, I have expanded this expression out. And now I'm ready to take the derivative. And the thing that's going to make us happy about this is I have 1, 2, 3, 4 terms. I can do them one by one because I have addition and subtraction between them. So derivative time. Okay, this 7 comes for the ride. What is the derivative of natural log of something? It's 1 over it, right? 1 over that something times the derivative of what was in here. What's derivative of what's in here?
1.
1. Okay, I don't need to write that 1, but I'm going to put it there just so you understand that I'm using chain rule there. And I'm done with this first one. Plus, okay, 4 comes for the ride. Derivative of natural log of 2x minus 1 is 1 over 2x minus 1 times what?
2.
2, the derivative of what's in here. Okay, move on. Minus 2. Okay, derivative of natural log of x is just 1 over x. And finally, minus 8. Derivative of natural log of something is 1 over that. Times the derivative of what's in here. What's the derivative of what's in here?
3x plus 3x plus 1.
Plus 1 in parentheses, right?
Mhm.
Okay, I'm going to clean this all up. We're done with the derivative, but I'm going to clean it up. Oh, hold on. Trying to. My phone's in my pocket. Okay, so I'm going to clean this up. I'm going to put this 7 up top here. So 7 over x plus 1. Let's see, I put the 4, then 2 up here, it becomes an 8. So plus 8 over 2x minus 1. On this next one, I just pop that negative 2 up top, or I'll just put a 2 up there and keep it negative out front. This one, I'll pop the 8 up here and I'll pop this up here. So it'll be minus 8 times 3x squared plus 1 over x cubed plus x. That's y prime. So if you would have tried this by doing like, not doing these properties and just going after this, this would have been a real mess. Because again, you would have had quotient rule. Within the quotient rule, you would have had product rules. And within the product rules, you would have had chain rules. And it would have been really, I mean, it's doable, but it would have been, there would be plenty of rooms for mistakes. Here, if you just know the properties of logs, would you all agree that the derivatives, when we got to this point, the derivatives were pretty clean because it's just little natural log derivatives and we were done? Yeah. We never had to do a product rule, never had to do a quotient rule, right? We had some chain rule. We did have some chain rule. Like we had a little chain rule here, we had a little 2 pop out here, you know, so it was there, but it wasn't like to the scale that it would have been had we had to do this. So do you see that there's kind of a value in this logarithmic differentiation? It's just another way to attack certain problems. It won't work for every problem. It works specifically for problems that involve natural logs, where you have a lot of products and quotients inside and powers, because then you can use the properties to split, right? Understand? How about the first problem we started class with? This problem would not have been good for logarithmic differentiation, because even though we have a log, we don't have products or quotients in here. We do have a power, but do you think you can pull that 2 out? What do you think? Is that 2 acting on the entire thing in here?
No, it's just the x.
Yeah, it's just the x squared. So you can't just pull the 2 out. And since this isn't a product, we can't split it apart into 2 logs. It's not a quotient, so you can't split it into 2 logs. So really, this problem was not. This problem doesn't lean towards the logarithmic differentiation technique. And the derivative wasn't that bad. It's just 1 over that derivative of the inside. We're done. Okay, you ready to see another one? Do one more. Okay. Y equals the natural log of the cube root of x plus 1 to the 5th over the square root of x minus 1. So what needs to be very evident to everyone here, or very clear to everyone here, is that the thing that's inside the natural log is all of this stuff. Okay, so this is the argument of the natural log function. It's all the stuff inside, right? So since it's inside, I can use properties of logs if possible. So does anyone see what I need to do first?
You can turn the cube root into an exponent, which would be 2 over 3.
1/3.
1/3.
Good. So the first thing we have to see is that this cube root really means we're raising all of that stuff on the inside to the 1/3. So that's just what the cube root means. The cube root means raising something to the 1/3. And just to remind you, if you have the nth root of something, that's the same as x to the 1 over n. So since we had the cube root, it became to the 1/3. If it was the 5th root, it would be 1/5. Okay, still no derivative, right? I'm not taking derivative right now. That's not ready. Now what?
Can't you move the 1/3 out front of?
I can move the 1/3 out front because everything in here is being raised to the 1/3. So I can bring the 1/3 out to the front. Now I still have all this. inside. Okay, what now?
Now you can split it up into like 1/3 natural log x plus 1 to the 5th minus the bottom part.
Okay, so you're saying that because I have division here, right? I can split this into 2 logs with subtraction between them, right?
Yes.
Now, when you do that, you have to be real careful because you had a 1/3 out here, didn't you?
Yes.
And that 1/3 is going to have to impact both the logs that we're about to create. So I'm going to put a set of parentheses here. Oh, wait, what happened to all my stuff? Did it just like erase? Yeah, it did. 1/3 is going to multiply times both the logs. So the first log I get is going to be the numerator. So it's going to be the x plus 1 to the 5th. And then minus, because division becomes subtraction of 2 logs. And then what about this next one? It's the denominator, right?
Yeah,
It's the denominator.
write it as x minus 1 to the 1/2.
Yeah, let's write the square root as to the half. So instead of writing square root of x minus 1, I'm putting x minus 1 to the half because we're going to pop that 1/2 out.
Yes.
And we're going to pop this 5 out. So we have 1/3. Okay, 5 natural log of x plus 1 minus 1/2 natural log of x minus 1. So that was the property that the 5s can pop out. Or so the 5 can pop out and the half can pop out. Before I take the derivative, I still haven't taken derivative, I'm going to go ahead and distribute the 1/3 through. So I get 5/3 natural log of x plus 1 minus 1/6 natural log of x minus 1. Now I'm ready for the derivative. So the derivative of this should be, well, 5/3 comes for the ride, and the derivative of natural log of x plus 1 is 1/x plus 1 minus 1/6 times derivative of natural log of x minus 1 is just 1/x minus 1. By the way, there was some chain rule here, but the derivative of both of the insides is 1. So that's why I didn't have to worry about popping any numbers out the backside of these. And you can leave it like that, or you can go ahead and put the 5 on top and distribute a 3 through the bottom. And on this other one, you can have a 1 on top and then maybe like a 6x minus 6 on the bottom.
You don't care if it's in either form, like non-simplified or simplified?
You mean like this top one or bottom?
Yeah. Does it matter or no?
No, I don't care. I mean, in all honesty, like in calculus, we always like to keep constants out front, just because if we need to differentiate again, it's just easier to keep the constants in the front. But either one, they're both the same. So, okay, what do you think? Do y'all see how these properties of logs can be useful when differentiating things that have logs, right? In some scenarios, it seems like it's useful. Yeah, hopefully you're sold on that. So I know Brian brought up, like, do you have to do this? You don't have to do it, okay? Because you could have taken the derivative of this without doing anything, any of the properties. It just would have been uglier and it probably would have been harder. But now we're about to shift gears. Remember I told you there's kind of 2 different types of logarithmic differentiation. This one was pretty straightforward. Just use properties of logs and get to an answer. The next one I'm going to show you, you have no choice but to use logs, right? There's nothing else you can do. So let me show you something before I actually get to the problem. I'm going to put up 2 things here for you. 2 different functions. And let's just discuss the difference between these two in terms of their derivatives. So what would f prime of x be?
4x to the third.
Or x to the third. That's just power rule, right? Power rule. We've been using that forever now. Now, g prime of x.
It's going to be the rule where it's going to be like 4x times.
4 to the x.
Yeah,
4
sorry.
raised to the x
Um,
times.
is it just natural log of a?
Not natural log of a, so natural log of 4.
Yeah.
So that that's from this right here. The derivative of 4 to the x would be 4 to the x times natural log of 4, and then times the derivative of x, but derivative of x here for us is 1. So this right here is an exponential, right? So there's a big difference between taking the derivative when you have x on the bottom, right? So here is our variable, and here is a number. When we flip it and put the number on the bottom as the base and the variable as the exponent, the derivative is different, right? Agreed? So it all depends. Which of these two methods we use depends on where the x is, right? So where's the x? Understand? So what about this function? What if I tell you y is x raised to the x, and ask you to find y prime? Now, in all of your studies, college algebra, pre-cal, you studied all these different functions. You never studied this function. You never looked at it. We intentionally stayed away from anything like this. So let's just go look at it. Let me graph it on the computer. Let's ask the computer to graph y equals x raised to the x. There it is. It's not a parabola, right? It just kind of weird. It kind of comes down and goes back up. Yeah, that's what x to the x looks like, all right? So it should make sense that we should be able to go to some value, like let's say 2, go up here, and find the slope of that tangent line. We should be able to do it, but we're going to need to be able to take the derivative. Understand? But we have a big problem, because for the first time in our lives, we are seeing kind of a combination of both of these, right? It's like on one hand, you could say x is in the bottom, but then you don't have a number up top. And then over here, you say, oh, well, the x is in the top, but then you don't have a number on the bottom. So this is neither a power function, nor is it an exponential function. It's neither one. It's something new, it's something different, okay? So the way you want to kind of think about this is that the exponent is some function of x, right? X is a function of x. And the denominator, the base is some other function of x, right? They're both functions of x. Here, the bottom is a function of x, the exponent is a number. Here, the bottom or the base is a number, and the exponent is a function of x. Anytime you have this, where x appears both in the base and exponent, we have to use logarithmic differentiation. Okay, that's what we have to do. But you don't see any logs, do you? There aren't any logs anywhere, are there? Do y'all see that there's no logarithms here? So what we do first is we take the natural log on both sides of the equation. So I'm going to take the natural log of y, and I'm going to do the same thing on the right side. I'm going to take the natural log of x to the x. Now, the reason why I did that is because there's a property of logs that we've already used that says if you have x to a power, what can you do with that power?
You can get that power out.
Power out front, right? And again, this has nothing to do with derivatives right now. This is purely just algebra. I'm just kind of rewriting the problem. So now it becomes natural log of y equals x times natural log of x. I could put that x in parentheses if you'd like. Okay, so now look at the right-hand side of this. Do you see we have x times natural log x? That you can take the derivative of, right? That you should be able to do derivative because it's a product. Do you all agree? Yes, yes, yes. Okay, but the left-hand side of the equation is no longer y. It's natural log of y. So what we have to do at this point is implicit differentiation. So what I mean by that is this. I'm going to take the derivative with respect to x on the left side. And then I'm going to take the derivative with respect to x on the right side. All right. I'm going to do the right side first because that's the part that most people are comfortable with. If I ask you to take the derivative with respect to x on the right-hand side, we all see product rule, right? So we're just going to do the little product rule here. The derivative of x is 1 times natural log of x, then plus, what's the derivative of natural log of x?
1 over
1 over x. And then times x. So we did a little like, here's f, here's g. We did f prime g plus g prime f. There it is, right? That's what we just did. And I'll go one line further. I'll clean it up. This is just natural log of x plus 1. Right? That's what this is. Because the x is canceled, you just get a 1. Now, this is not the derivative, okay? Be real careful here. This is the derivative of the right-hand side, but what about the left-hand side? I waited on that. You have to do this implicitly with respect to x. So what would the derivative of natural log of y be? So what's the derivative of natural log of anything?
1
over that anything, whatever it is, right? So 1 over y. But then chain rule says now you must take the derivative of what was inside that log function. So the derivative of y. And what is the derivative of y with respect to x?
dy over dx.
dy dx. Right, you just had a test on implicit differentiation. So do you see that's all I'm doing here? Except now I'm incorporating the derivative of the natural log of something is 1 over it. And then dy dx. This dy dx is really like y prime. That's all it is. So here's where we are. We have 1 over y times, I think I'm even going to write y prime here instead of dy dx. These are the exact same thing. And this is what we're trying to find, right? We're trying to find y prime. So I need to get rid of the 1 over y over here. What could I do on both sides of the equation to get rid of 1 over y?
Multiply by y.
Multiply by y. And then take this side and multiply by y. And over here on the left-hand side, you get y prime. And on the right-hand side, you get natural log of x plus 1 times y, right? But what's y?
X to the x.
X to the x. So I'm going to replace y with x to the x. And that's your derivative. Okay, so you have to make that connection that why is this because of that. So the derivative of x to the x is natural log of x plus 1 times x to the x. Any questions? I'm ready to give you another one. Go ahead.
Sorry, can you please explain one more time the left side of where we did the implicity? Right there, yeah.
Okay, so we're trying to take the derivative of natural log of y, right? We're trying to take derivative of this. So what's a derivative? What is the derivative of natural log of anything?
1 over whatever.
That anything, whatever it is, right? So 1 over y. Yes? So you're done taking derivative of natural log. Now you have to take derivative, you have to take derivative of what was in here. So what is a derivative of y with respect to x? That's just dy dx, right?
Right. Okay. Thank
So
you.
times dy dx. But that's just y prime. So that's why I just replaced it with y prime.
Thank you, sir.
Okay. Any other questions? I'm going to give you one now. It's going to work exactly like this one worked. So I'm even going to leave this work up here for you to look at if you need it. And here's the problem I'd like for you to do. Y equals sine x raised to the 1 over x. I want you to find y prime. And I know this is only the second example. I'm having you do it yourself, but I will again stress to you, the base of this has x in it, right? The base of that thing has x. The exponent also has x. So you can't use power rule and you can't use the exponential rules. You must use logarithmic differentiation because x's appear both in the base and exponent. Why don't you take 5 minutes and see if you can get this? Do it the same way we did it here. Good luck. I'm going to start showing the work. Okay. Okay, there it is. So let's talk about it. Please let me know if and where you have questions on this.
Could we just stop a step before it? Right there.
Oh, yeah, I mean, no, because you still have to get the y on the other side.
Oh, okay.
So you would have to, I mean, you could leave it like this and then put y out here, but you have to remember to replace y with this because that's what y is. Like if you don't turn the cosine over sine into cotangent, that's all right. Does anyone have any questions on anything I did here?
Where do you get that 1 over x after the cosine x?
Product rule. So when you take derivative of natural log of sine x, it's 1 over sine x times cosine x. That's chain rule on that. And then to finish off the product rule, you have to have the derivative of, or sorry, the first function. Remember, it's like f prime g. So here's f prime g plus g prime, that's this, times f, which is this.
Okay.
Everyone okay with where I got negative 1 over x squared?
Yes.
Okay. That's, I'm going to show it, but I want everyone to remember that's really x to the negative 1. And so when you take derivative of it, it becomes negative 1 x to negative 2, which is really negative 1 over x squared. And I would suggest that for those of you going on to Cal 2, you just kind of burn that into your brain. Kind of like, you know, the derivative of sine of x is cosine x. You should know the derivative of 1 over x is negative 1 over x squared. Okay, well, what do you think?
So for problems like these, you would have to put the natural log of y equal whatever, as well as natural log. Right?
What, as well as natural log, what?
Or whatever, like, see how like you put natural log of y is equal natural log of.
Of whatever's over here.
Yeah.
Yes.
Okay. 'Cause
You're
kind of,
essentially doing natural log on both sides of the equation.
okay.
And you're only doing that because then you can use the property that this can drop out front. And once you drop it out front, it'll turn into a product, which you can do the derivative of. So there's a give and a take. You have to introduce the natural log, but then it allows you to actually differentiate it.
Yes, okay, thank you.
Okay, good. All right, so that completes 3.3. You should be able to do the rest of the homework for that section. Make sure you do. And we're going to move on. All right, so the next section in the book is 3.5, inverse trigonometric functions, which we are not going to do. That's something I told you you would start Cal 2 with that. And so if you go back and you think about what you learned in pre-cal. So in pre-cal, you learn all these trig functions: sine x, cosine x, tan x, then all the reciprocals: cosecant x, secant x, cotangent x, right? And you study these, you graph them, look at their periods, amplitude, you know, all these different things, right? What we've done in this class is we've now said, look, we know the derivatives of all of these. We know that when you take the derivative of sine, you get cosine. We know when you take derivative of cosine, you get negative sine. When you take derivative of tangent, you get secant squared x. And for each of these, we have derivatives, right? That's what we've learned here. But in pre-cal, you also study each of these functions has an inverse: the arcsine function, the arccosine function, the arctangent function, right? And there's 6 of those. You study those in a pre-cal class. We, in a calculus class, we do want to know what is the derivative of this? What is the derivative of that, right? All of those. That you will start Cal 2 with, okay? We are not going to do it here. And then after that, in Cal 2, you study what are called hyperbolic functions, which you have not seen at all. And so we define in Cal 2 what a hyperbolic function is. And after we define what they are, we say, what are the derivatives of those hyperbolic functions? And it turns out that there's a bunch of hyperbolic functions. You have sine hyperbolic, cosine hyperbolic, tangent hyperbolic, cosecant hyperbolic, secant hyperbolic, cotangent hyperbolic. So there's 6 more functions. Each of those has derivatives. And then you study their inverses. So each of those 6 hyperbolic functions has 6 inverse hyperbolic functions, and each of those has 6 derivatives. So you're going to wind up with another 12 functions. Like right now, hold on.
Is h a function or is it a number like e and pi?
H is to let you know we're talking about the hyperbolic sine function as opposed to the sine function.
They're also on your sheets.
They're all in the formula sheets. Yeah. So what you wind up having at the end of the day in Cal 2, what you wind up having are the 6 basic trig functions, their 6 derivatives, the inverse trig function and their 6 derivatives, that's 12. And then you have the 6 hyperbolics and the 6 inverse hyperbolics in each of their derivatives, so you have another 12. So you wind up having 24 derivatives of all these different types of trig functions. Okay, so we are not going to do that here. Save that for Cal 2, something to look forward to. We are going to get into 3.7, which is called indeterminate forms and L'Hopital's rule. L'Hopital, that's the way you say that, L'Hopital. I know it looks like La Hospital, but it's L'Hopital. And this is a very, very important rule, all right? I would say one of the most important things that you're going to come out of this class with is L'Hopital's rule. Like if you come out of this class and you don't know L'Hopital's rule, you know, dead man walking, if you've heard that phrase before. You know, it's like, you don't know this, you're going to be in trouble later, all right? It'll catch up to you real quick. It's a beautiful rule. It's very powerful. And I'm going to show it to you, and then you're going to be like, wow, okay, that's pretty awesome. Well, I don't know if you'll think it's awesome, but.
It is beautiful.
Okay, so there's bad news. You remember how we were doing limits in the early parts of this class? We were doing limits. And sometimes when we do a limit, we get like 0/0, and we'd say that's bad. We have to do some algebra, right? Or if we got like infinity over infinity, we'd say that's bad, and we'd have to do some algebra, right? And I gave you that sheet. Remember I gave you the sheet, the limit summary, where it said what to do if you get these different scenarios? Yeah? Okay, L'Hopital's rule is a rule that allows us to calculate limits much easier than we were doing before. So here's how the rule works, and I'm not going to get too much into, where is it? There it is. I'm not going to get too much into why it's true or anything like that. We're just going to do it. But the important thing to know about L'Hopital's rule, important thing, you can only use it when you take a limit and get 0/0. You can only use it when you take a limit and get infinity over infinity. Those are the only times you can use L'Hopital's rule. So we've seen limits in the past that get 0/0, right? And infinity over infinity. When you see that, L'Hopital's rule is fair game, all right? If you see anything else, you can't use L'Hopital's rule right away. You might have to do something algebraically, but this is the form we need in order to apply the rule, okay? Now, what is the rule? The rule says that suppose you're taking a limit, okay? Suppose you're taking some limit. Who cares what x is going to? You're just taking a limit, and when you take the limit, you get the 0/0, all right? So you have some function on top divided by some function on the bottom, and when you do it, you get 0 on the top and 0 on the bottom. L'Hopital's rule says that, well, if this limit exists, okay, if there is an answer to this limit, it will be equal to the limit of not f over g, but the derivative of f over the derivative of g. So let me illustrate this in an example. Let's say we're trying to do this back from the beginning of class. What is the limit as x approaches 2 of x squared minus 4 over x plus 2? Okay, let's just think about how we did this before. What we would do is we would do the evaluation theorem first. We just replace all our x's with 2's. We'd get 0 on the top and 0 on the bottom. We'd say that's bad. And we would say we need some algebra or some trick, right? That's what we said, algebra or trick. And does anyone remember what the algebra would be here? What algebra would I do to get this to work?
Negative sign, x minus 2 instead.
You do
2 plus 2, it's going to be 4. It's going to be 0/4.
not sure what you just said because you cut out.
Oh, I was saying where you put x plus 2, right? If we distribute 2 in there, is it going to be 0/4?
Oh shit, my bottom is minus. Sorry. See, I've been making these mistakes all day. Jeez. That means I'm ready for the weekend. Thank you, Dilpreet. This should be a -2, or else we would have got 4, and 0/4 would have been 0, and the answer would have been 0, and we would have been done. But it's supposed to be -2, my mistake. So now we get 0/0, yes? So the algebra that we did back in the day was to realize we had a difference of squares. And then what we would do is factor, and then one of the factors cancels. And now when we do substitution in here, we just get 2 + 2 is 4. Right? That's the way we did it before. What L'Hopital's rule is telling us is that instead of doing that, since we're getting 0/0, what we can do instead is say that this limit should be equal to the same limit.
X to the 4th power.
Well, the derivative of this. So, Robert, what the? Jeez. Maybe I just need a drink or something. I don't know.
It should be 2x and then
2x on top, and then on the bottom, derivative of the bottom, which is just 1, right?
And then you replace that with the 2, and then that gives us 4.
And now we replace the x with 2, and we get 2 times 2 on top is 4. 4 over 1 is 4, and we get our answer, which is the same answer. And it's not a coincidence. That's what the rule says. All right. So look, when I do this step from here to here, I need a way of letting you know that I just used L'Hopital's rule. Okay, so somewhere in here, I just need to kind of indicate to you that I just used L'Hopital's rule. So the standard notation for this, and books do different things. Some books put an H here to let people know, hey, I'm using L'Hopital's rule. Sometimes they put an H and they circle it. And sometimes they put an L here. And sometimes they put an L and circle it. I do L and circle it. L for L'Hopital. The H is for L'Hopital too, but just the H, right? The H in the L'Hopital. So that right there is just indicating to everybody why this became this, because I applied the rule. And I could only apply the rule because I got 0 over 0. Okay? Now, do you remember this one? I gave you this limit way early in the class. Limit x approaches 0 of sine x over x. And I told everyone to memorize this one. Do y'all remember what the answer to this is? What I told you it was? No? Everybody fails.
1 or?
It's 1. It's 1. And I told you to remember this. Okay, I just said memorize that. And the thing is, at the time we did it, I couldn't prove it to you, because if you try and do this limit, sine of 0 is 0. And of course, if x goes to 0, you get 0 on the bottom. This is bad. We need to do some algebra, or we need to do a trick. But there is no algebra trick that you can do. And please don't tell me you're going to just cancel the x's, because that's not allowed. Okay, so we were stuck at this point, right? And so I just told you, hey, memorize it. I'll explain it later. Well, today's later. Okay, so now what I'm going to do, because I get 0 over 0, I'm going to write limit x approaches 0, sine x over x. And I'm going to say, I'm going to apply L'Hopital's rule right now. And this now becomes limit x approaches 0 of the derivative of the top, which is cosine of x, over the derivative of the bottom, which is 1. And now if I let x go to 0, what's cosine of 0?
1.
1. Okay. Let's do another one. Okay, remember the problems like this? Limit x approaches infinity of like 4x squared plus 1 over, let's say 9x squared minus x plus 2. You remember us doing limits like that? X is going to infinity. So where's the numerator headed?
Infinity.
Infinity. Where's the denominator headed?
Infinity.
Infinity also. Infinity over infinity?
Bad.
Bad, right? But now we have L'Hopital because we're allowed to use L'Hopital on infinity over infinity. So I can rewrite this. I can say that this will equal, by L'Hopital's rule, the limit as x goes to infinity of the derivative of the top. What's the derivative of the top?
8x.
8x over the derivative of the bottom, which would be
18x minus 1.
18x minus 1. Now, at this point, we have to see what happens now when we take the limit. Let x go to infinity. What would happen up top?
Infinity.
We get infinity again. Over what happens on the bottom?
Infinity.
Infinity again. Well, great. We have infinity over infinity. That's bad. But we have L'Hopital again, right?
The
So
second
we can just
derivative?
use L'Hopital a second time.
Okay.
So I'm just going to run L'Hopitals on this one more time. What's the derivative of the top?
8.
8. Derivative of the bottom?
18.
18. And that is just a number. That's just what?
4 over 9.
There you go. We're done.
So you just keep basically taking the next derivative until you no longer get infinity.
Well, yes and no. You keep doing it as long as each time you do it, you get infinity over infinity or 0 over 0. You can't just keep on applying the rule over and over and over and over until you're ready to stop. You have to stop when you no longer have 0 over 0 or infinity over infinity. Like on this step right here, well, when we did it the first time, we still had infinity over infinity. When we did it the second time, we no longer had infinity over infinity.
So
We had a number over a number, and that's just an answer. That's just a number.
what would happen if you have one infinity and one number?
Okay.
Algebra.
What if we did limit x goes to infinity, and we have x squared plus 1 on top, and on the bottom we have x cubed plus x. So we get on the top, this goes to infinity. On the bottom, it goes to infinity. That's bad, right?
Mm.
Okay, so we do L'Hopital one time. Let's see what happens. 2x on top,
Mhm.
3x squared plus 1 on the bottom. Still have infinity over infinity. Do it again. Top,
2.
bottom.
6x.
Okay, now what's happening here? Where's the top headed?
Fixed number over infinity.
Fixed number. Bottom, infinity. What happens when you have a fixed number over infinity? Where does it go? Goes to 0.
Okay.
Okay. What if it would have worked the other way around? What if I would have given you a problem? Let me see, I'll do it in a different color. What if I would have flipped this and done the x cubed on top plus x, and on the bottom, the x squared plus 1?
Well, let's work it out.
So you get infinity over infinity, right? We do L'Hopital. Right? Infinity over infinity still. L'Hopital again. 6x over 2. Now the top's headed to infinity and the bottom is fixed. Where's that headed to?
Infinity.
Infinity. Think about it. Your numerator keeps getting bigger and bigger, and your denominator is just a number. So, I mean, let's say the denominator is 2, right? So what happens if you take a big number and divide it by 2? Well, it's some number, right? Now let the numerator get bigger. It's divided by 2. It's going to start getting bigger and bigger and bigger. It's going to just take off to infinity. Make sense?
Yeah.
We'll do one more, and then I'm going to ask a very profound question. Limit theta goes to 0 of sine theta over tangent of 4 theta. So let's check what happens. Sine of 0 is 0. Tangent of 4 times 0 is 0. So tangent of 0 is also 0. And this is bad. Does anyone remember how we did this back in the early parts of this class?
Didn't we like separate them? Like,
Yeah, we had to like peel it all apart and then try and like, we would say, oh, it'd be real nice if we had like a 4 theta here, and we just introduce a 4 theta over 4 theta. And a lot of students struggle with that. And I don't get too much into it. I usually put one on the test, but I don't get too upset if students can't figure it out, because I know what's coming later, which is this. All right. So now you can apply L'Hopital's rule. So this will become limit theta goes to 0, derivative of sine of theta, cosine theta, right? Derivative of tangent of 4 theta, be careful. Tangent of 4 theta is what? What's the derivative of that?
4 secant squared
4 secant squared of what?
theta
4 theta.
4 theta.
Right, so the derivative of tangent of 4 theta is secant squared of 4 theta, but then you have to do chain rule derivative of 4 theta, which is 4, and I just put it out front. Now let theta go to 0. What's cosine of 0?
1.
1
1, okay. Now on the bottom, it's going to become 4 times, now be careful here, this really means secant of 0 squared. That's what this really means, right? Because you're going to replace theta with 0, so that's 4 times 0, 0. You're going to do secant of 0 and then raise it to the second power. What is secant of 0? Well, secant is 1 over cosine, isn't it? So isn't that 1 over cosine of 0?
Just 1.
And cosine of 0 is 1, so that's 1 over 1. So that's just a 1 down here. So this 4 times 1 squared, that's just 1/4, which is what you would have gotten had you gone through all that other work of trying to like figure out what to include. I would show you what I'm talking about, but remember I lost all my notes earlier a couple of weeks ago when my computer had a freak out. I'd bring up all my old notes and show you like how much work we had to do. So what do y'all think?
Woo! I love
Thank
this.
you. Thank you, Daniel. So I know that students will often sit here and wonder why it is that I tortured you with all of those limits. Why not just have shown you this to start? So why do you think I didn't just show this to you right away?
Because we wouldn't understand.
To build character.
To build character. We wouldn't understand when, I guess, if we're asked to take the derivative of something. Or
Yeah, so what would have happened if I told you, hey, when we're doing this limit, just take the derivative? You'd be like, deriv what? What's a derivative, right?
Mhm.
Like you wouldn't have known what I'm talking about. Because if you think back at the way this course has progressed, we started this whole class with the idea of the limit. And then from that, we built the definition of the derivative, right? The derivative, what we said is that the derivative is just the limit as h goes to 0 of f of x plus h minus f of x all over h. That's what the derivative of a function meant at some value x, right? So we said, oh, let's talk about limits, and that sucked. And then we said, hey, this one particular limit is this thing called the derivative. And then after that, we got the rules. And after we got the rules, that was all your like power rule, product rule, quotient rule, chain rule. And now we've got like implicit differentiation, all this other stuff. And what we're doing now is we're saying, hey, guess what? We can actually use all of this to come back and do limits again, because L'Hopital came up with the rule or a theorem that allows us to do it. So it's really not because I didn't want to show it to you. It's that you can't get the horse, the buggy in front of the horse. Have you heard that saying before? Don't put the buggy in front of the horse.
Yeah.
Right? We had to do this in order. And now that we have this tool, we can come back and use it. So that's why. All right. How are we doing on time? 2:20. As you might imagine, go ahead. What?
No, you're good. Sorry.
So we're gonna probably start getting ridiculously difficult problems
Not ridiculous.
to use L'Hopital on.
Absurdly difficult. Not ridiculous. Probably absurdly difficult. No, they won't be difficult. I mean, they won't be. Well, they'll be what they are. Okay. So let's try one. Okay, that's going to look a little weird initially. Okay. So how about the limit That's not a limit, that's a natural log. How about the limit as x goes to infinity of the natural log of x over the cube root of x? So yes, I mean, Danielle, in some respect, there is no way you could do this limit without L'Hopital's rule. Like, you're not doing it, okay? You're not. So L'Hopital, so yes, they are more difficult in that sense. Like, we couldn't touch this without L'Hopital. Okay, so let's just check on what's happening first. So this first one is very important that you understand what's happening here. As x goes to infinity, what is natural log of x doing? And that takes us back to last class. Last class, when we were talking about exponential functions in the very, very beginning of class, I said, hey, remember, I don't know why this is not coming up. Hold on. Okay, I'm gonna save this. I gotta reopen that. It's not wanting to open. Okay, do you remember when we were looking at exponential functions and I said, look at the graphs, look at the way they behave. As you go to infinity, this goes up, but to the left, it goes to 0. Remember we talked about all that? It was because I knew this was coming with L'Hopital. So look, when we talked about log functions, we said that this is what a log function looks like as long as the base is bigger than 1. This is what it looks like. And if the base is less than 1, it looks like that. In this particular case, we're talking about the natural log of x. What is the base of this function? What is the base of this log?
E.
E. The base is E. Remember I told you with the typewriter, it sucked, so they decided to stop writing it with the E and just wrote ln instead. But you need to remember it's E. And E is bigger than 1 because E is 2.718. So our graph of natural log does look like this. So what happens as you go to infinity? As you go to the right, what does the natural log function do?
Get bigger.
It's bigger, it goes to infinity, right? You need to know that or else you can't do this problem, right? You don't need to actually write anything down. You just need to actually know that that's what's happening. So I know that the numerator is headed to infinity. Okay, what about the denominator? Okay, if I take a number, x, and I let it get huge and take the cube root, it's still going to be huge, right? So that's going to infinity. So I have infinity over infinity. I'm now allowed to use algebra, a trick, or L'Hopital's rule. I'm going to go with L'Hopital. So this should be equal by L'Hopital to be limit as x goes to infinity. And a little warning here. You've all become so good at quotient rule, right? Like you're all like masters of the quotient rule at this point. Quotient rule is like derivative of top times the bottom minus derivative of the bottom times the top over the bottom squared, right? You've like learned that, you've got it burned in. With L'Hopital, it's not a quotient rule, okay? You're just taking derivative of top and bottom separately. Like this is the only time you can ever do it is when it's L'Hopital. So I'm gonna do derivative of the top, which is just 1 over x, and then the derivative of the bottom. And I recommend that you look at the bottom before you take its derivative as x to the 1/3, and then take its derivative. So that would give me 1/3 x to the negative 2/3. Is that okay?
Yes.
I have to figure out now what's happening as x goes to infinity. So in order for me to do that, I'm going to clean it up first, just so it looks a little nicer. I get 1 over x on the top over 1 over 3 x to the positive 2/3. So I left the 1 over x on the top like this. And then on the bottom, I rewrote this as 1/3 is 1 over 3. And then the negative exponent here, I dropped it down to the bottom with the 3. Do you all see that?
Yes.
Okay. And now don't take your limit yet. Let's do some algebra here. We have a fraction divided by a fraction, right?
Look
A
it up.
fraction divided by a fraction. So we can multiply by the reciprocal, can't we?
Yeah.
So limit x goes to infinity. Okay, it'll be 1 over x times the reciprocal of the bottom. The top is 3x to the 2/3 over 1, like that. And the reason I did that is because I can now use properties of exponents to figure out what that is. X to the 2/3 over x to the 1 is x to the 2/3 minus 1, which is x to the negative 1/3. So just properties of exponents, seeing that over that, right? Yay, 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 nay.
Yeah.
Okay, so what I've done here is I've taken this part in yellow and I've rewritten it with this, x to the negative 1/3. But because it's negative, I dropped it down to the denominator and made it positive 1/3. But positive 1/3 really means cube root of x. Now, all of this algebra I just did was so that now I can take a limit and see clearly what happens. Do you all see what happens now?
Yes.
Top goes to a fixed number. Bottom goes to infinity, which means this limit goes to 0. Yay. All right. Ten minutes. I'm wondering if I have enough time to do the one I want to do next. I don't think I do. Let's do this one. Let's do this one. I have enough time to do this one. Limit. Let's go x approaches infinity. X tangent of 1 over x. Okay, we haven't done one like this yet. So let's talk about what happens when x goes to infinity. This goes to infinity, yes? But then we have multiplication times, okay, tangent of 1 over infinity. What does 1 over infinity go to?
0.
0. So this is going towards tangent of 0. Do y'all see that? And where is tangent of 0? What is tangent of 0?
1.
Tangent of 0, nope. Remember the tangent function looks like this.
0.
Pi over 2 here and negative pi over 2 here. So at 0, it's 0. So this is headed to 0. Okay, I just said an important word. I said this is headed to 0. Headed to 0. I said headed to 0 because we're taking a limit. And when you take a limit, you never actually get to the places you're going. You're just approaching them. So what we have is we have one piece of this. This front part is getting huge, right? This is becoming a huge number. And we're multiplying that times this number, which is getting very, 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 it's 3 varies small, okay? So what happens when you take a very, very big number, a huge number, and multiply times a very, very, very small number?
Cancel out.
Well, you don't know, do you? You don't know how huge this is, and you don't know how small this is, right? You have no real indication of like, this could be a billion, right? Which you'd be like, man, that's a billion, that's huge. But this could be like one like trillionth or something like that, or a trillionth of a trillionth. This could be so much smaller than this, that this one dominates this one. Or it could be the other way around, where this one dominates this one. The big thing is we don't know, okay? This is still an indeterminate form. This is just like getting 0 over 0, infinity over infinity. We just don't know what the answer is, okay? So do you all understand we are stuck at this point? We can't do anything. And we cannot use L'Hopital's rule, because for L'Hopital, you must have 0 over 0 or infinity over infinity. And we do not have those, right? Do y'all see that? We have infinity times 0 multiplied. We have no division, right? So how do we approach this? Here's what we do.
Algebra of some sort.
We're going to do a little bit of algebra. Yeah. It's going to be not hard algebra, but it's going to be like weird algebra. That's the original problem. We know that this thing goes to infinity times 0. I know I can't use L'Hopital yet. But now what I'm going to do is I'm going to be very clever, and I'm going to pick one of these. And for this problem, I'm going to pick the x, and you'll see hopefully why I'm doing this after I do it. I'm going to leave the tangent of 1 over x here, but I'm going to rewrite that x that used to be out front. I'm going to rewrite it on the bottom as a 1 over x. Now, do you agree that this is the same exact problem as this one? Do y'all see that? Yes? Because you have a fraction down here now, this x would flip up and then hit this thing, and it would just become this, right? So I just chose to drop the x down as a 1 over x, just so it would look different to us visually. And now what I'd like to do is talk about what happens to each of these individually. So as x goes to infinity, we already know that this goes to 0 and tangent of 0 heads to 0. But where does this denominator go now?
0.
0, fixed over infinity, right? Fixed over infinity goes to 0. And now we have infinity over infinity like we were hoping for, so that we could use L'Hopital's rule. So that's the trick. If you see infinity times 0, or even the other way around, what you have to do is you have to grab one of those. Now, you could either have grabbed the x or the tangent of 1 over x and drop it down to the bottom as 1 over it. I picked x because 1 over x on the bottom is nice and clean. If I were to have taken the tangent to the bottom, it would have looked like this. Y'all see the difference between if I leave x here and drop tangent, I get this. But if I leave the tangent and drop the x, I get this. And I would prefer to work with this. Why? Because I'm about to take the derivative. That's why.
Could you not change tangent into sine over cosine?
Yes, you could. Yes, you could change it to sine over cosine. You mean down here?
No, like from the very beginning, yeah.
Yeah, you could have. You could. It doesn't change the problem though. You still have 0 times infinity. Like that won't go away.
Okay.
Okay, you ready for a derivative? I'm doing L'Hopital, derivative of the top. So watch carefully. Derivative of secant something is secant squared of that same something times the derivative of what's inside, chain rule, negative 1 over x squared. I just told you a minute ago that you should memorize that. Be comfortable with the idea that the derivative of 1 over x is negative 1 over x squared over what's the derivative of the bottom.
Negative 1 over x squared.
You get a 1 over x squared again. And oh my goodness, do y'all see what I see?
So
Negative 1 over x squared.
You what?
Okay.
You're right. Now let x go to infinity. If you let x go to infinity, this whole thing becomes secant squared of, let's see, 1 over infinity goes to 0. But that's just really 1 over cosine of 0 squared, but cosine of 0 is 1, so that just becomes 1 squared, which is 1. So the answer is 1. So in the beginning, we had something that was getting huge and something that was getting really, really small, and they're like battling each other. And what happens is at the end of the day, they compromise and they get closer to 1. I'm going to show you the graph. So if we take the graph of x times tangent of 1 over x, ooh, that's crazy looking. There's the graph. What we're interested in this graph is what happens is we're going to infinity, because that's what the limit was. And you can see that as I move out to the right, well, let me graph y equals 1 here. So there's the horizontal line y equals 1. And you can see that that's kind of like acting like like an asymptote. Our function is approaching that line. As we go out to the right, it gets closer and closer and closer and closer and closer. It never gets there. But as we move to the right, it just keeps getting closer and closer and closer and closer. It doesn't look like it's getting closer now, but it is. Okay, just get closer and closer. Okay, you see what we just did? All right, so for your homework, what I suggest you do, because we can't do every problem in this section yet, I suggest you try, and I think you're going to run into some problems. Let me see what the homework assignment says real quick. So we are in the section on L'Hopital. Why is this so big? There we go. L'Hopital.
But we have the homework solution videos though, right?
Yes, you do. I'm just saying there's problems on here I haven't talked about yet. So, you know, I wouldn't want to send you to go do problems that I haven't shown you how to do them. I would say don't do anything past go up to 25. Like 26 and on, we need to discuss some things still. And you might still have some problems with 25 because I just did one example. Okay. So work on that. Next class, we will come back and we're going to do more L'Hopital's rule, and then we're going to get into chapter 4.
Yay.
Hey, week's over. Another week is over. How many weeks do we have left? This is getting close. 1, 2, 3, 4, 5 weeks. No, is that right? Today's the.
We lost a week to the blizzard.
Yeah, 1, 2, 3, 4. So we have 4 weeks of class left. That's 8 meetings. We have 8 meetings, and we're supposed to have an exam in there. So we really only have 7 more class meetings. And yeah. Well, we got a lot of work to do. Don't fall behind at this point, because the train will leave the station. You'll be standing there with your ticket going, what? Okay, do your homework. Okay, you have a great weekend.
Thank you, Professor.
Thank you, sir. Have a good weekend.
You too.